Production of X-rays. The lab setup shown here was designed by Coolidge, and hence it is called Coolidge tube. It contains a highly evacuated glass bulb containing a cathode, which is a tungsten filament, and anode, which is a target made up of metal of high atomic weight. The pressure inside the bulb is maintained at 10 to the power of -6 millimeters mercury. When the cathode is heated by passing a current through it from a low-tension battery, it emits cathode rays. These rays are nothing but electrons. The filament is surrounded by a molybdenum cylinder, which is kept at a negative potential to the filament. This repels the electrons further, and hence the electrons form a fine pencil beam at the center of the cylinder. This pencil beam is also accelerated by the cylinder towards the target. The target is made up of a copper block in which a piece of tungsten or molybdenum is fixed. High thermal conductivity is used to carry away the heat generated to the cooling setup. Here we use copper, which is a good conductor of heat and can take the heat away from the molybdenum metal towards the water cooling system. The target is also tilted at an angle of 45 degrees, causing the electrons to hit at an angle. This will produce the X-rays almost perpendicular to the electron beam. A very high potential of 20 kV is applied between the source and the target. Due to the high potential difference, the electrons are accelerated towards the anode and it hits the metal. When it hits, the kinetic energy is transferred to produce X-rays. The intensity of the X-rays depends on the number of electrons striking the metal target. So, if we can increase the rate of electrons emitted by the filament by increasing the current flowing through the filament, then we can increase the intensity of the X-rays.
X-rays are powerful enough to fly through many kinds of matter as if they are semi-transparent, and they're particularly useful for medical applications because they can make images of organs, like bones, without harming them, although they do have a small chance of causing mutations in reproductive organs and tissues like the thyroid, which is why lead aprons are often used to block them. When X-rays interact with matter, they collide with electrons. Sometimes the X-ray transfers all of its energy to the matter and gets absorbed. Other times, it only transfers some of its energy, and the rest is scattered. The frequency of these outcomes depends on how many electrons the X-rays are likely to hit. Collisions are more likely if a material is dense, or if it's made of elements with higher atomic numbers, which means more electrons. Bones are dense and full of calcium, which has a relatively high atomic number, so they absorb X-rays pretty well. Soft tissue, on the other hand, isn't as dense and contains mostly lower atomic number elements like carbon, hydrogen, and oxygen. So more of the X-rays penetrate tissues like lungs and muscles, darkening the film. These 2D pictures are only useful up to a point, though. When X-rays travel through the body, they can interact with many atoms along the path. What is recorded on the film reflects the sum of all those interactions. It's like trying to print 100 pages of a novel on a single sheet of paper. To see what's really going on, you would have to take X-ray views from many angles around the body and use them to construct an internal image. And that's something doctors do all the time in a procedure called a CT, computed tomography scan, another Nobel Prize-winning invention. Think of CT like this. With just one X-ray, you might be able to see the density change due to a solid tumor in a patient, but you wouldn't know how deep it is beneath the surface. However, if you take X-rays from multiple angles, you should be able to find the tumor's position and shape. A CT scanner works by sending a fan or cone of X-rays through a patient to an array of detectors. The X-ray beam is rotated around the patient and often also moved down the patient's body, with the X-ray source tracing a spiral trajectory. Spiral CT scans produce data that can be processed into cross-sections detailed enough to spot anatomical features, tumors, blood clots, and infections. CT scans can even detect heart disease and cavities in mummies buried thousands of years ago. So what began as Röntgen's happy accident has become a medical marvel. Hospitals and clinics now conduct over 100 million scans each year worldwide to treat diseases and save lives.